this very kind introduction. And also many thanks to Raul and his group for organizing this nice conference and for inviting me once again. It's always a pleasure to be here. So today I want to talk about some joint work together with Manolis Iorgoulis, who is a professor of numerical analysis in Athens, Shengwang Liu, who is a postdoc in Delft, Jasper Roux, who is a PhD student in Delft, and Kostas Maragdakis, which some of you here know, I think, he used to be a postdoc in Athens, and now he is faculty at the University of Aegean, so another nice place. And this is about, well, essentially deep learning methods for solving PDEs. So most of the thing will be developing the method and discussing, how you can do things and how you can compute things. And there is a last slide with some theory, so to get in line with the title of the conference, which is applications. So theory and applications, I'm doing it the other way around. Okay, so I think everybody in this audience knows about jump models and diffusion models and rough models, so I don't think I should motivate my talk too much. So I decided to motivate not at all. So I cut directly to the problem. And the problem we are interested in is solving a PDE or a PIDE of this form. Okay, you have the derivative with respect to time plus some operator which is acting on the function. And then, well, I mean, by a change of variables, you can translate your terminal payoff into an initial condition. Okay, you are interested in solving this PDE or PID, and the operator is an integro differential operator of this form, where you have here some diffusion coefficient, some drift term, interest rate, and then in the end you have some jumps. Okay, so this is a super classical problem in mathematical finance and in many other fields of science, obviously. And the particular applications we have looked at is, on the one hand, basket options in a jump diffusion models. Okay, so where this the diffusion term is relatively simple, but then you have jumps acting, and then you have to deal somehow with the jumps. And we have also looked at the classical European options like single asset call options, but now in these rough or lifted diffusion models, where you have some hidden dimensionality coming from the approximation. And I know Christian says that you can do it already with 2 factors, but well, for illustration purposes, we take more classical approximations and we need 20 factors. So in both problems, there is some hidden dimensionality, and this is why you are interested in, this is why the problem becomes essentially interesting. Okay, so just to motivate what is going to follow, there is a very classical approach to solving this type of problems using neural networks. So this is this deep Galerkin method, or DGM, of Sirinian and Filiopoulos. Take the key that you are interested in solving and turn it into a quadratic minimization problem, and then feed this in your SGD to find the solution. Okay, well, this is super simple. This is somehow super intuitive, and it works pretty well. So it's a general purpose method. You don't need to think about the context, about the problem, it works with everything, basically. Okay, on the other hand, there are some things that you can always improve by looking at specific applications or specific dynamics. So one issue you have in mathematical finance is that the operator here has a second derivative, and this is usually costly when you try to do the computations. And the other thing is, well, I mean, they are solving everything in a space-time cube, so it is not cube. So it is not clear why this is the most natural formulation, and you don't want to do something like time stepping. Okay. So we were motivated by works of like Manolis and co-authors from Athens, and also there is a group in Korea, which is, well, they had more or less a paper with the same ideas around the same time published. And the idea is, well, to rewrite the PDE as an energy minimization problem, which has somehow 2 effects. The one effect is that you are getting rid of the second derivative, which is costly. And the other effect is that, well, now you have a cost function which is somehow natural to your problem, right? The L2 norm is nice, but, well, it sounds a little bit artificial. Now you're getting one which is tailored to your problem, and you can do things a little bit easier. And then the other thing is you want to introduce some time stepping, And the motivation for time stepping is that, well, I mean, as you're going to train one neural network for its time step, but then you can use the values from the previous, the values of the neural network in the previous time step as the initial guess for the next time step. And this, well, in theory at least, but also in practice, it should decrease the training time. Okay, and also, I mean, your initial function is essentially, I don't know, the payoff of a call option or a basket option, which is something not super complicated to approximate. Good. Okay, the issues that are arising is, first of all, the operator is not necessarily a symmetric self-adjoint operator, so you have to think a little bit how you're going to deal with this, how you're going to translate this into an energy minimization problem. And then if you consider jumps, you have to think about how you are treating this integral operator. Okay, so first of all, what do you do about, well, how do you treat the operator? Well, the solution is obviously very classical. You're going to split the operator in two parts. The one part is going to be the symmetric part and is going to give rise in an energy. The other part is a remainder, and then you have to do something with the remainder. So this is again just repeating. This is the integral differential of an operator that we are considering. Using simple calculus, essentially, you can rewrite it in this term, which is a symmetric term. Then you get this first, like you have second order terms, you have first order terms. You have here the interest rate, and then you have this, the integral operator, which we denote by the sign nu from now on. And from here, well, you can do several things, but one thing that we are doing is that you are defining here this LU, which is a symmetric operator, where you take the second order derivatives plus this interest rate term, and you are putting everything else in the remainder. Okay, I mean, there are many ways in which you can split it. This is the way we have chosen. Okay, one comment which is due here is that in the integral term, you can also find the symmetric part. So you could also think that, well, I can take the symmetric part from this integral term, and I can stick it in the symmetric part of the operator and then generate an energy in that way. At least in our computations, this seems to be creating some instabilities, because you are going to place this part in the symmetric term and the other part in the non-symmetric term. And these two things are not communicating very well with each other, because you're going to treat it differently when you discretize things, okay? Exactly, that's what I mean. I mean, mathematically, you can split them in two parts, but computationally, I mean, if you keep them together, you have cancellations and the method is more stable. If you separate them, it looks fancier, but for us, at least, it is not working. Maybe other people are smarter. Okay. Sure, welcome. Okay, so simple example in order to, well, not complicate things, but just at least show how things are going, what we are doing with this operator is, we consider the Heston model. I assume more or less everybody in the room knows the dynamics of the Heston model. So this is the asset price, and this is the variance process. Well, I mean, it's a simple application of Ito formula to find out what is the differential operator which corresponds to this dynamics. It is the one written here. And then it is again an exercise in, essentially in, I don't know, Ito calculus to split it in the way that is suitable for us. So here we have the second derivative with respect to the asset price, which is giving rise to these two terms. The one is second order, the other is first order. The green term, which is the second derivative with respect to variance, is also giving two terms. And finally, this mixed derivative here is giving rise to four terms, and then you put them accordingly in the different terms. Okay, so somehow by the color you can follow what goes where. So this part is coming to the symmetric term, and the other part is going to the linear term, etc., etc. Okay, good. Okay. So now we have formulated the PDE in the way we like. So we have a derivative with respect to time. We have here the symmetric term, and we have the remainder term. And what we are doing now is we are taking, well, some time interval, we are cutting it in, we are subdividing the time in smaller time intervals, and we want to introduce some discretization. So we are going to work in general with the so-called implicit-explicit PDF discretizations. And right now I have forgotten what PDF stands for. Backward differentiation formulas, I guess. Yeah.
Oh, thank you. So the idea then is to use an operator splitting.
Mm-hmm.
Okay.
Yes. I mean, you have split down the operator in two terms, one symmetric and the remainder term. And now in the discretization scheme, this is your time derivative. And then from the remainder term, you're really solving implicitly. And the symmetric term you are treating implicitly. And the remainder term you are taking from the previous value. So you are explicit in that. Okay. And well, okay, these things are somehow known. So for P is 1, you get this backward Euler scheme. For P equal 2, it's still called this BDF2. And
so somehow for the LUK term, you're going to use some kind of deep rates given the other part, or
kind of what?
Deep rates with this energy minimization for the LUK, and for the other, you just time step it somehow.
Exactly, yes.
Okay, cool.
No, it's coming in the next slide, so you are one step ahead. Okay. So, well, you know, our friend Babis has worked on, you know, stability and analysis of this type of discretization schemes. Okay, so as Raul just said, I mean, you're now interested in solving this PDE, and now for every term, you're basically creating a term in the respective cost functional. So from the time stepping, you are getting this L2 type of difference. From the symmetric operator, you are getting you are getting this integral term where you have associated here this Dirichlet energy functional. And for the last term, you are actually integrating just with respect to U. So the one term is really implicit, the other term is explicit, and you just get a value from your previous steps. Okay, and then, well, sorry. And now you have created, yeah?
On right, yeah, sorry. No, just to follow. So you have these somehow stages, right? For the U,
yeah,
right? And you're creating it. And now you write a cost functional that is a black CU view that contains all of them somehow, and you can decouple it by the. Okay, I was just checking where the coupling is, and the U that is in blue also appears in the red one, right? Beta P times U somehow. Just trying to follow essentially the minimization if it's decouples or not, right? How do you do it sort of progressively?
You are solving, I mean, at every time step, you're computing this value and this value. And in the green term, there is no U to compute. In the green term, you're just getting the value from the previous step.
Exactly. So the blue and the red are coupled because of the U.
Yes, exactly.
Okay, so it's not purely somehow the true energy from the symmetric problem that you get for U, but also there's a coupling with the previous values of U that you get from the red when you solve for the U, right? In the implicit step. I'm just trying to follow the coupling there. There's an energy minimization in the epsilon of U dx, right? That would be one term, but that's not the only one. It also couples with the red term at the beginning.
Exactly. You have the energy minimization here, and then this is the part you're getting from the time stepping.
Exactly. So the U will be a balance between minimizing the energy and being
exactly and minimizing
to the previous values. Okay, okay. I just wanted to check. And the green?
The green part is a known value from your previous time step. So you don't need, I mean, in the actual time step, you're not computing it. You're just inserting the value, and then you go forward.
But somehow the U appears there too, right?
But it is the U from the previous time steps.
There's a U there. That's why I was tracking the.
Maybe the U.
Because in the green part upstairs, I didn't see the U, right? First line, when you say implicit, explicit, the green term doesn't contain the U.
No, but this is coming from the minimization, right? You're integrating this term. Sorry. So you are referring to this U here, which is missing from here.
Variation and get a linear term out of it.
Yeah.
Okay.
It's just from the calculus of variation.
Okay.
Yeah.
Thank you.
Welcome. Good. Okay, where was I? Okay, so this is now your new cost functional, which is somehow tailored to your problem, or it is going to follow the specific problem you are trying to solve. And now what you're going to do is you're going to introduce an artificial neural network, and then you train the neural network by classical stochastic gradient descent or whatever variant of this method. Okay, so in the end of the day, what you're really inserting in your stochastic gradient descent is this discretized cost functional, and then you're generating samples which are these xi, like uniformly on the domain you're considering, and you're progressing until you're somehow finished. Okay. So now, some things about how you can use information you know about the problem at hand in order to make your training faster or more efficient or somehow going to the correct values. So the one thing is, you need somehow to truncate the domain, and then you need to decide what happens, especially in the jump case, in case you get a value which is, in case the jumps are sending you outside of the domain. So what we are doing is the following. We consider, in general, some domain omega that we want to solve the PDE inside this domain. But now the effective domain from which we are really solving the PDE is this shaded region. And then for everything outside of the shaded region, the idea is that you know that for large enough moneyness, your option price is going to behave linearly in the underlying asset. Okay, so you're going to use this information, and instead of having a boundary condition, you are going actually to essentially replace it by this. So the idea is that once you get a point, anywhere, you're going to project it on, if it is not inside the domain, you're going to project it on this green curve. And then, in order to get a value for this random point, you're going to get a value from the boundary of your domain, and then you're going to extend it linearly. So somehow asymptotically, this is doing exactly what your option price should be doing. This is the one point. And the second type of information you can use in order to make your problem simpler is the following. So at least this is the main idea is basically that if you want to approximate something, it is better to approximate something small than something large, because then your error is going to be even smaller. Okay. So the idea is that you're going to decompose the function you want to approximate. Let's call it this UK. This was the ANN approximation of the true solution of the PDE. You're going to decompose it in, what like economists or finance people would call this intrinsic value of the pay of the option and the time value of the option. Or I think I have it the wrong way around. This is the intrinsic value, this is the time value. Okay, and the idea is you're going to get a lower bound. Sorry, you're going to get, this is somehow the lower bound for your payoff, and this is what you are essentially computing in the end. Okay. And the lower bound is, from classical option pricing theory, we know that the payoff is a lower bound for the option, or whatever option, and then you have somehow a time value which is coming from interest rates, and you're going to approximate this, since the step function is not somehow very compatible with neural networks, you're going to still keep the payoff function and approximate the rest with a sigmoid function. Okay, so in the end, you have a smooth approximation of this intrinsic value by the payoff plus this thing here, which is the sigmoid approximation of the step function. Okay. Good. So this is somehow the global architecture of the solution. You want to solve, you want to compute the solution at these points in every time step. You're going to project them to something which is either, well, if they are not inside the domain, you're going to project them on the boundary of the domain. You compute this, the intrinsic value, which is essentially the lower bound. And then you also compute this add-on factor, let's call it, in case it is needed. And then with the rest, with these values which are somehow inside of the domain, you are going to use, you're going to compute a solution from that, and it is going to give you now the time value of the option. And then you put all the pieces together, and you are back at, well, let's say the global solution for your option pricing problem. Good. And well, for completeness, I mean, what happens inside these layers where the artificial neural network is working? Here we are just copying these TGM layers from Sirignano and Spiliopoulos. So these are exactly the same operations, and they have been tested, and at least for PDEs, they are working extremely well. So there is no reason why you should change this. Okay. So, well, okay, some numerical examples. So this might or might not be a video. Yeah, okay, I think if we had Acrobat, it would have been a video, but now it is just a static picture. Apologies for that. Well, okay, so here we consider this lifted Heston model with just one parameter. So this is essentially a reformulation of the standard Heston model. And we are computing the price of a European call option in three methods. This TDNM stands essentially for this energy minimizing we are discussing here. DGM is this DGM method, and COS is this, well, this COS method of Fang and Osterle, which is religiously popular in Delft, so we have to use it since we are in Delft. Okay. So, well, but dimension one is not very challenging, so there's not so much to discuss here. And from the error plot, we basically see that the error is small, so well, not really a lot to discuss. We can do the same thing now with 20 factors. So we opened this paper of Alpi-Chabert, we copied everything, and then we tried and tested. And well, it is still working extremely well in 20 dimensions. And you see also the error. I mean, it is a little bit bigger than the DGM error, but essentially it is super small, so you would accept it. The problem here is the following. The problem here is the following. I think it is I think in the Eduardo's paper, there are two sets. The one set has zero volatility and the other set has like non-zero volatility. And what we have observed, so if we want to be truthful, is that as the volatility is increasing for n equal 20, then the error of the method is also increasing. Okay, so up to 5 factors, we are still okay. But for more than 5 factors, the error is increasing at levels where you would really not accept it and not use these prices for trading. So my intuitive explanation why this happens is because you have essentially, you have a hypoelliptic PDE, and this is starting to bite you at some point.
Sorry, a quick question. When you say factors, 5 factors, what do you mean? I mean, you don't mean the dimensions, right?
No, I don't mean the dimensions. I mean that you have, I mean, so if you come back here and you imagine this lifted Heston model of Alpi-Chabert, he has these Vn factors that he is adding, these VINs. So you take 20 of those. So if you take up to 5, you are still okay, even with non-zero correlation. But if you take 20, and then as the correlation is increasing, your error is increasing. And at least my intuitive explanation is that you still have two Brownian motions and you're trying to cover the space like a 21-dimensional space with two Brownian motions, and at some point it is simply not feasible. But well, we have some ideas of how you can treat this, but until we try and test them, well, this is just speculation, right? But Christian knows much more about this than me, so maybe we can discuss later. Okay. Good. So some tables also about computational times. I mean, of course, you know, one has to be careful with this type of comparisons, right? Because you have to be sure that you're not trying to cheat or you're not trying to favor your own method. But I think Jasper here has done a nice job of at least being fair with everybody. What we can clearly see is that this energy minimizing method is not, so the training time is not significantly increasing as you increase the dimensions. So you see this is almost always between 6 and 7. The factor in front is 6 and 7, while for the DGM, this is increasing quite fast as you increase the number of dimensions you consider. And on the other hand, well, in terms of, so once you have trained everything and you're trying to execute, you're executing super fastly, while in a plain course implementation, the computational time is becoming prohibitively slow as you increase the number of factors you take. Okay, not because cost is slow, but because you have to solve what is it, a 20-dimensional Riccatio D, and this is going to cost time. But of course, I mean, cos is an exact method, right? So you are actually using cos as your testing bed for everything else. Sorry, I'm going the wrong way. I mean, you see here, even in the good cases, the error is comparable. When our method stops performing, it stops performing. Right? Okay, so this somehow comparison of computational times in the case all methods are performing. Yeah. Yes. Okay, so let us take a second example. So let us consider, well, a simple jump diffusion model. The simplest case you can consider is this Merton model, where you have essentially the Black-Scholes dynamics. So you have some volatilities and some, now you're in a multi-asset setting. So you have constant volatility between your assets, you have correlation. And then you also have jumps, and the jumps are arriving according to Poisson intensity. And then once they arrive, they are distributed according to multivariate normal distribution. In order to make life simple, we have one Poisson process governing everything. So once there is a jump, all the assets are jumping simultaneously, but then the jumps are not the same. The jumps then follow this multivariate normal distribution. So you can view this also as a way of correlating the assets. You're also correlating them by, or you're making them dependent by asking them to jump at the same time. Now, from the numerical point of view, the challenge here is coming from the integral operator. So for every sample point in your, for every sample point that you are using for your stochastic gradient descent, you have to compute the integral. And now it is a question, how should you efficiently do it? Okay. Now here we have tried two things. The one thing is to use like classical sparse grid integration that people here know very well. So you can do some, I mean, you can use the fact that it is, your density is normally distributed. So you can try to do a singular value decomposition and then change variables to align everything with a matrix at hand, and then apply a sparse grid integrator. So this was the one thing we tried. And the second thing we tried is to train a second network that is going to learn just the values of this integral. Okay, so you have here an unbiased estimator of this integral operator. And then what you're essentially doing is you say, well, now I have one set of parameters, like neural network parameters, that is going to approximate the option price. And then I have a second set that it is going to be trained just on approximating the values of this integral. And then you get a second term in your cost function that you are using. Okay. In terms of performance, they seem to be closely matched. So this is just a plot of the integral. So this is just a plot of the integral you are interested in computing as a function of moneyness. So you see they are both relatively close to each other. What we can observe is that the neural network is, well, obviously faster and it scales better with the dimension. But the behavior in the tail, so for large values and small values of moneyness, it is not as good as the sparse grid. But the sparse grid is somehow stopping relatively. I mean, it is becoming then a boundary of how high you can go in dimensions. Okay, so these are some plots from, these are now plots of option, like basket option prices, first considering 5 assets, okay, expired in 12 months. Using this discretization, the second order discretization is obviously faster than the first order discretization by a factor of 3, if I remember correctly. And now you're using this sparse grid approximation for treating the integral operator. And what you can observe is that, well, between Monte Carlo and this ANN, the prices are closely matched. And this is now the difference between the payoff and the option price at time 1. So you see everything seems performing well, and the error is relatively small. It is of the order of 10 to the minus 3. And the picture is more or less similar if you go to 15 dimensions and you use now the same time-stepping scheme, but now you're treating the integral operator by the artificial neural network and not by Gauss-Hermite integration. Okay, again, you see a small error and somehow good performance or good comparison between Monte Carlo and this and our method. Okay, finally, a few words about theory. So up to now, everything is just, well, you're developing the method, you are trying in some example for some parameters, and it seems to be working well, or for some others it is not working well, but now you don't know why. And we are also working on some theoretical results. So what we have achieved up to now is you can show, first of all, that if you have a single layer neural network, then as you increase the number of neurons, the cost function is going to 0, which is what you would expect. And then you can also show that, you know, the approximate solution coming from the neural network is going to the true solution. Okay, so if you consider this as a static picture, it means that you can find the neural network that is going to approximate your PDE. And then inspired by a paper of some Cohen and co-authors, you can also show that in this framework, the outcome of the trained neural network is going to converge to the true solutions. But okay, we are still working on this, so it takes some notation and some discussion to put everything in pure mathematics. So I just write everything in words. Okay. So at least also from the theoretical point of view, you have some justification that in certain cases, the method is really going where you expect it to go, and you're not just lucky with the parameters or with something else. Okay, so these are the 3 papers I have discussed. So the first one with Manolis and Kostas about the jump diffusion model. The last one, which is also out with Jasper about this rough or lifted diffusion models. And the theoretical paper is still work in progress. So let's say in 1 month, it will be on the archive, which means like by Christmas, it will certainly be on the archive. Okay. So yeah, that's it from my side. Well, thank you very much and plenty of time for questions.
Thank you.